My name is Moyou. I'm a Senior Solutions Architect at NVIDIA. So I work with retail clients on getting different types of Gen AI models to production and things like that. So I kind of want to walk you through this journey of enhancing your intuition about the LLM inference workload. So I won't show you a ton of code that you've seen in some other presentations, but I assure you after coming through this presentation, you'll be able to read research papers and understand all of the different packages that very large folks are using at scale. The other thing, if you stick around to the end, I will give you free GPUs, because I know that's why everyone is actually here. Cool. All right. So in terms of understanding, oh, there we go, LLM inference. So let's just look from left to right. So what I'm saying very simplistically, I'm asking this LLM, sending a prompt, write me a presentation on LLM inference, so I look smart, I keep my job at NVIDIA, okay? So what I want you to look at is that box of the GPU. I'm actually putting it on the GPU. So just remember, every time we prompt an LLM, what are we doing? Occupying GPU memory, okay? Rule number one. And then on the end, I'm generating tokens one at a time, T1 through T4. So I'm showcasing those timestamps for you. So no matter how fast you see any speed of an LLM in your life from whoever, it's always one token at a time. That's the beauty of it. And I'm just showing you one request. So imagine this, millions of requests, hundreds of millions of requests happening. And then I put LLM inference is, so just remember that in this conversation, I've kept track of everything that I've said. So every new word that I told you, I'm basically just remembering everything that I said before. That's why these tokens have to go back onto the GPU every single time that they're generated. So an LLM is basically just us, but to some degree a lot slower. Maybe smarter, who knows? All right, so in terms of processing blocks intuitively, first when a prompt comes in, I'm first going to convert it into some representation that a model understands. A model does not understand text, it works on numbers, so there's a process to do that. In terms on the GPU itself, I have this thing called model weights. That's occupying GPU memory, so that's what you're also paying for. And then I have this process where we initially process your prompt. So if you spoke to me for 10 minutes and I didn't say anything and then I had to respond, I have to really process what you said for 10 minutes, okay? And then once I understood what you said, then I start generating tokens and giving you back a response. That's why the longer the prompt you send, all of a sudden there's just like this lag, and all of a sudden tokens start to spew out, because it takes some time to understand. And once the LLM says, okay, here are the tokens I'm going to give back to you, those tokens are not things that you understand, it has to convert it back to whatever language that you're converting in. Okay, so here are the technical terms. When you go read all of these papers, so you'll see tokenization and detokenization. So that's converting from text to a token, from a token back to text or code, whatever the case may be. Prefill is the stage where the attention mechanism is computed. There have been a lot of great talks at this conference about attention. That's an insane area of research in terms of how fast you can do things, utilizing different pieces of memory, moving data around faster and faster. Really cool, interesting area of research. And then decode and generation, I'm just highlighting that it's one token at a time. That's why you see the tiny blocks, right? So just keep that mental model in your mind. From there, I want you to let's look at how text is going to actually get transformed for an LLM to start understanding it. So at the top, I'm giving you this proxy. So think of a token in an LLM as 4 characters of text, right? It's not exactly that, but that's a good proxy for you to move forward with. So from there, sorry, I'm blocking my own thing. I'm showing you 2 arrays, right? So I have tokens, T1 through T capital V. So for instance, Llama 3 has 128,000 tokens. And then I have a corresponding numeric index, because I'm lazy. I don't want to use the token. I just want to use the number to represent the token. And then my job is to say, okay, I'm going to go from your input prompt, whatever crazy formatting you send to me, and I have to convert that into a vector of token IDs, right? That's the goal in the first part. So here's what it looks like. I say, make me sound smart, and make me sound smarter. And this is what the LLM sees, a vector of numbers. I want you to notice that I put this ER suffix here, and it has an extra token, just to reinforce to you that an LLM token is not a human understandable word. Typically, it's some chopped version of it. And the way that people develop tokenizers, so for instance, Llama 3 is trained on 15 trillion tokens. So they do an optimization problem. They say, okay, what subset of characters can re-represent 15 trillion tokens plus whatever other languages that people are going to send into my system, okay? So that's why they probably have 128,000 tokens. So now I went from text to a corresponding vector of token IDs. Inside of the model itself, there's an embedding table. So each one of those tokens, 128,000 tokens, has a corresponding embedding vector. Many folks in machine learning, know the benefits of vectors. They allow models to do things like similarity, et cetera, et cetera. So there's an embedding table. So what do I do with this thing? And that embedding table, these are parameters of the model. So these are trained during pre-training. So they'll figure out what are the best embedding models, and think of it as arranging tokens in some embedding space, right? So a vector is just a list of tokens, a list of coordinates, essentially. So these are just high-dimensional coordinates of 128,000 objects, essentially. So if I look at, make me sound smart, I'll convert to a vector of token IDs, and from there, I just fetch the corresponding embedding vectors, and lo and behold, I get a matrix, right? So every time you talk to an LLM today, you're just putting matrices on GPUs. What are GPUs very good at? Crunching, large and large matrices very, very fast. Now, so just to reinforce that, this is what you're actually paying for when you go to any LLM provider. Even if you are paying to self-host yourself, you are just packing more and more GPUs on, more and more matrices onto the GPU. So the larger the matrix, you can expect sort of an increase in time of processing. So that's what we're going to cover coming up soon. All right, so we talked about tokens, text to tokens. Now what are we actually going to do with the token itself? The attention mechanism, I always like to make sure that people have a good intuition in their mind. So every time a token is generated, I'm actually computing this thing called the attention mechanism. And the proxy you want to keep in your head is like, okay, when I'm going to say the next word, I'm going to say what was important in what I said before. Not all the words that I said before were important. They were like key things that reinforce the next word that I'm going to predict. So that's what the attention is trying to do mathematically on this big matrix of tokens that you've put in. Okay, and the reason why I'm showing this is this thing called KV cache. KV cache is also the thing that you're paying for when you pay an LLM provider, both for input and output. So I'll talk about why it's sort of priced that way. So I'm saying make me sound smart, and we're going to generate this first token LLM. Okay? So I'm repeating the 3 matrices that I had before, make me sound smart. I'm just repeating it 3 times. It's not actually copied 3 times. And we get to this thing called the model weights. So if you've ever wondered what an LLM model weights looks like, it's actually just, it's more complicated, but there's 3 of these matrices. There's also a bias term as well. But the main ones are query, key, and value. And that's how it's going to actually compute similarity across words. So all we're going to do is just do this matrix, multiply, and then I'm going to get 3 corresponding other matrices, query, key, and value. So you hear this thing called KV cache if you look at any paper, any sort of inference package, and that's what that means, key and value. So it's when I take my input data, I multiply it against my corresponding weight matrices, and I get that output. That's my intermediate representation. So every time you do a matrix multiply, it's a projection. So you're actually putting those coordinates into a different space. So now we basically just ask the LLM, hey, what do you think about this text? And this is what it's telling you. Hey, I think this is what the text kind of looks like in my understanding. And then this goes off and does a bunch of math. And that's, there are many different schemes for attention. But the key thing I want you to take away here is each of these, each word turns into 2 different vectors, right? So I'm actually replicating data on the GPU. And this is going to be important for me to compute the next word. So this is when you first send a request to the GPU or any LLM system. Now, we just generated that LLM token. Let's assume that. So now I'm actually going to put that back on the GPU and try to prove to you that we need this thing called the KV cache. So as I shared before, I have to understand every single thing that I said before, just like humans, in order to predict what the next word is. So I'm saying I'm fetching the corresponding embedding vector for LLM. Notice I didn't repeat the matrix that I had for all of my tokens, the initial prompt that came in. So I multiply that against the weight matrices again. Note that there are actually like 32 of them, so I'll come up on that soon. And instead of pushing all of that data back to the GPU, I just push that token into the GPU. And then instead of recomputing everything that I said before, that's like saying someone spoke to me for 10 minutes, I said something, and then I replayed the entire conversation back to myself, and then went again, and it's obviously very slow. So with this thing called the KV cache, I'm keeping state of everything that I said before, so the next token that gets generated is blazingly fast, right? And think of this gets even more complex as you start thinking of when models do not fit on a single GPU. They don't fit on 8 GPUs in a node, they fit across multiple nodes, and this thing called the KV cache, this is what it actually looks like. So Llama has 32 heads, right? So I have 32 sets of these matrices. So when a token comes in, it's going to do that matrix multiply against 32 sets of those matrices and other matrices as well. But this is so anytime you read documentation about attention heads, I want you to have this sort of image in your mind. So you can appreciate like the larger and larger models that you use, like the complexity of this math becomes more and more. So the speed of your interconnects, your speed across nodes becomes very important. Your speed is important for you. Let's see on time. Good. All right. Going to push you a little bit. So in Prefill is me understanding what it is that you asked. So what I'm going to try to walk you through is the complexity of when you go beyond a single request and why it's actually difficult to optimize this for speed. So when a request comes in, so I'm sending a prompt, I'm going to compute this prefill. I need to understand what the heck it is. The LLM needs to understand what I asked. Okay, cool. It understood what I asked, and it started generating a token, right? So this is a single request. Now, here's where it gets really interesting. Somebody else sends a request while I was talking to the LLM. I'm having that conversation. I don't want you to have that conversation. But in order for me to get my next token, so the way that it works, it's called an inference loop. So there are only two states that an engine, so an engine is just an optimized model. There are only two states that it does. It's either generating a token or it's computing attention. So it's either understanding or responding. Think about it that way. So when you send 10 pages of a PDF because you want to play the RAG game, I now have to wait for this thing to understand 10 pages of a PDF before I get the next word. Right? So these were some of the early challenges that were happening. So when you see, I'll show you some stuff in the inference server. Actually, we're going to look at that right now. So there's this really cool paper. Highly recommend you read it. It's called piggybacking. So piggybacking means when the current person is in generation, so they're getting the tokens that they want, and I am, as a new user coming to the system, I'm actually just going to try to piggyback on that computational workload. But that piggybacking has to be very efficient. So here's what it looks like. Just sort of brace yourself. Okay, so here's what this really means. Just pause. So I have 4 requests, A, B, C, and D. The subscript P means prefill, so just think I'm understanding. And then the D, the subscript D, just means decode. So you'll see D1, D2, D3, that's just token 1, token 2. So at the top, if you look, I want you to look at the relative sizes of the request. So look at the length of prompt A versus the length of prompt B. So when prompt A and prompt B come in, I have to wait for prompt B to finish because it's longer than A in order for both of us to get a token, our first token, right? So we got our first token, but hey, C and D snuck in there. So now we have to wait for C and D to get all the way through in order for us to get the next token. It's not a very good sort of user experience. So what chunk prefill says is like, okay, instead of, trying to appease the new user, I'm going to start processing your new prompt in chunks. So I'll only process this chunk, I'll start generating a token. I'll only process that chunk, but I could still get the current users what they need from that system, right? So these are some optimizations that happen inside of an inference server, and this is happening real time. So if you sort of look at this, notice I'm starting to break up this corresponding understanding phase. So prefill 1 and now prefill 2. So instead of trying to sit and try to understand the entire thing, I can just break up that understanding and respond to the user, right? So hopefully that makes intuitive sense. If you ever want to know how much GPU memory a model occupies, simply just take the size of the model, multiply it by 2. That is your FP16 memory. So here's an example. If you have a H100, that's 80 gigabytes. I have a Llama 8B. That will be 16 gigabytes of GPU memory, minus 16 gigabytes, and the rest of space that you have, which I think is 64, that's what you have for your KV cache. That's what you have to serve all of the users in your system. Why do you think people like H100s so much? It's because of this thing. So FP8 allows you to basically reduce that memory in half, multiply your speed almost by 2, technically. So now I get back an extra 8 gigs of memory in order to sort of serve requests to users. So this is why people like the Hopper GPU or FP8-enabled GPU. So I'll show you what those are at some point. Maybe make sure I check my timing. 4 or 5. Ooh, I need to move really fast. So yeah, okay. 1 second. Okay, so if you ever go to estimate the size of a KV cache just means what is the total number of requests that you can serve to a user given your free space and memory. That's what it looks like. I'll show you a blog that you can go read more. Please read this blog. It's a fantastic blog from NVIDIA. Covers a ton of concepts as well. So this will help you get through faster. So I'm going to move a little faster. For those of you that are running inference systems, not running inference models, running inference systems, you can leverage GenAI Perf. This is what we test, benchmark all of our models with at NVIDIA in terms of measuring different time to first token, latency, et cetera, et cetera. So let's just cover some of the metrics. So when someone says time to first token, how long did it take me to understand, plus until the first token was generated. That's what time to first token means. We have to monitor that to measure our efficiency of the attention mechanism. Second is inter-token latency. This is actually super important when it comes to when you're generating really, really long sequences. You don't want the spacing in between those tokens in terms of timings to be too wide, because then that means you're not as efficient anymore, right? Next one is time to total generation. How long did it take me to fulfill your entire request, get you out the system? Maybe, maybe not. You'll see this thing called input sequence length and output sequence length. And that just means how long is the input, how long is your output. And this is important for you when you go read benchmarks. Okay, here's a sort of intuitive thing. LLM inference and GenAI inference, but let's just focus on LLM inference. It's specifically different to, traditional deep learning inference. So if you deploy models on a GPU, like a computer vision model, please deploy more than one model on the GPU. You can maximize the throughput. That's how we used to maximize throughput, having multiple model copies, single inference server, higher throughput, more workers. But in LLM inference, more so at scale, you can pack more models on a GPU if you want to, if you have lower traffic. So you just have your model weights, that's occupying a certain amount of memory, lots of optimizations, people are trying to compress it, keep the accuracy, et cetera, et cetera. And the remaining space that you have is the individual requests of all of the users of your system. Okay? And this is not on a single GPU, this is like across multiple GPUs, across systems of GPUs, in the cloud, on-prem, more or less the same principle applies. This is the most important thing when it comes to cost. If you're putting GenAI in production, you want to be very conscious of these different patterns in your workload, right? So who is sending the longest prompts? Who is asking for the longest amount of tokens? That's typically the most costly use case that you use. So hopefully now you have an appreciation that when you do things with an LLM, what you're really doing is occupying GPU memory. So the more data you put on it, the more memory you occupy, the less requests that person can serve, so you pay correspondingly. And why is the price different across models? The bigger the model means the less GPU memory I have for requests, which means I need more hardware to serve X number of users in a reasonable amount of time, if speed matters. All right, so those are some use cases. And so I'm actually going to walk you through some. Here's just like a intuitive diagram, just to show like each person is going to send a different request and request a different amount of tokens. So the actual distribution, so a lot of times when people are monitoring systems, you would get these fixed inputs coming in and these fixed outputs coming out. With LLM systems, it's not like that. It's just these random things happening. And so for you to manage your memory at scale, it becomes very difficult. So there's a lot of optimizations you have to think about. Okay. So for those of you, if you're building an LLM tool, monitoring tool, this is good stuff. So this is, what I'm showing here is a 2D histogram. Follow me. 2D histogram of the inputs versus the outputs. Okay, so if someone said a 200 length prompt, or I think that's, what is that? 400 length prompt versus 100 to 100 out. Basically what we're trying to figure out is what is the actual distribution of input lengths versus output lengths. And there are different optimizations that you could do when you build an optimized engine file to almost kind of shrink the math so it runs faster. So if I know no one is actually going to send really long queries to my system, I could just shrink the engine, get some more. So, we're kind of hustling for GPU memory for tokens is essentially what we're doing. That's my scientific explanation. If you do time to first token analysis, a simple box plot, what this is actually telling us, especially for us at NVIDIA, is, hey, how efficient is your attention mechanism under load? So you've seen flash attention 1, 2, 3. How does flash attention 3 perform on a single request versus 300 concurrent requests coming into the system? And that helps us to analyze, because there's CPU components as well that go into, as the gentleman from VLLM was saying, right? A lot of pre-processing and post-processing happens on the CPU. So you need that to be in a really, really tight loop. Time to completion, sort of the same thing, but we're also looking at, okay, what is the decode efficiency and what is the actual attention efficiency when I commit? The other one that's interesting, yeah, time to first token-to-token latency versus token position. This is super interesting. Lots of things are interesting. As a token a sequence, output sequence gets longer and longer, I'm occupying more and more memory, right? And I have multiple people in that system occupying memory. We all know when you reach memory limits, things start to break down. So we like to see a consistent spacing between those tokens. So at capacity, if we can produce really long sequences and keep that same timing, we know we've written the software really well, essentially. Okay. And the other one, time to first token versus number of input tokens. This is sort of just showcasing the longer a prompt is, naturally, the longer it takes you to understand, just like a human. But we don't want that understanding to take exponentially longer, right? So we want to see almost like not a purely flat curve, but that slope shouldn't really go up. So that helps us to really optimize different things on the GPU. Okay, I'm going to talk to you. I have 3 minutes, so let's see how far we get. TensorRT-LLM and Triton. You can also run VLLM on Triton as well, just so that you know. Triton is an open source inference server from NVIDIA. TensorRT-LLM is a model compilation package for you to really optimize models on NVIDIA GPUs. We recommend it. And I'll show you NIM that uses both VLLM and TensorRT-LLM under the hood. So at a high level, if you use a FP8-enabled GPU, like a H100 versus an A100, you'll get significant benefit. And basically what's happening under the hood, we'll take your model or standard set of models, we'll rewrite it in TensorRT-LLM primitives. Those are actually quite optimized. And then we'll essentially create an engine and deploy that on Triton. Right? So I'll actually walk you through some of the features here as fast as I can. So some things. So this thing called FP8. So people like FP8 versus int8 because I get to keep the accuracy, but keep the memory of int8. So the accuracy loss with FP8 is actually quite minimal. I also have a slide in there as well. So in things with KV cache, so I could reuse the KV cache, I could compress the KV cache. Page KV cache just means I'm actually allocating blocks of memory instead of allocating smaller uniform blocks of memory. I'm almost 90% sure we have speculative decoding and everything in there as well. You have support for FP8, a bunch of different quantization schemes, in-flight batching. I'm going to show you what that means. Ton of different models in there as well. And there's really nice documentation to show you how to build and deploy the engines. And sorry if I'm rushing. That's just because I want to respect the other person's time. Okay, so this is kind of how it works at a high level. So we talked about tokenization, pre-processing. Many of you may have used TensorRT before if you were doing regular deep learning. So we took a lot of that deep learning compilation and added some extra things that happened in the LLM loop to make it more efficient. So that sampling and stuff like that is sort of what TensorRT-LLM itself handles, but it builds on a lot of the work that the TensorRT team did. This is a proxy as to what an optimized engine, very advanced as you can see. So this is why people really like H100s, H200s, and let me see, get the Blackwell. So once you go to deploy on Triton, so you build a TensorRT-LLM engine, there's a backend. Think of it as just like it can interpret that file. And Triton has what's kind of nice about Triton is you can launch multiple models and have a single inference server. But there's lots of cool stuff there. I think this is where the inference market is heading. So as you sort of scale out an enterprise, you want to be very aware of where the market is going. So a lot of people like FP8. Why? Just because you get half the memory, almost twice the speed. So what is Blackwell going to bring you? You know, a quarter of the memory, almost 4x the speed. So things like that you want to sort of get prepared for, depending on the scale that you're working at. These are the GPUs I recommend you focus on. If you're on Turing and Volta, I would like you to just move one level up to an Ada, L4. Ampere does not have FP8, so I want you to be very aware of that. So if you use A100s, you don't have access to FP8. So try to, you know, either do an L4, L40, or any of these GPUs. DJ, am I good on time, Jason? Or you're gonna kick me out? Jason, I'm talking to you. Am I good on time? I could take some minutes? All right, I'm going to steal it. OK, cool. All right, so let's look at KV cache and attention mechanisms. So there's some actually really cool earlier talks on people are just trying to hustle for GPU memory. They're like, OK, I don't want to use more GPUs. I just want to make it more efficient. So people are just doing a bunch of math to make attention more efficient. So one of the interesting ones is like windowed attention. OK, I'm only going to pay attention to the last 5 minutes that we spoke. After that, I'm not really paying attention. Sliding window is fairly similar as well, but this is just to showcase like you have some of these options inside of TensorRT-LLM. It's a software package, but I want you to have that intuition when you go to read the docs. OK, KV cache reusage, this is really important. Every time you go use one of the frontier LLMs, all of a sudden somehow it remembers what you just said, right? And remembers, you know, the 10 conversations that you had. So when you go ask it, what did I say before? This is also why it forgets, because it's a limited context. Also, context is your input and your output. So when someone says a million length context, that's all the garbage you put in and all the stuff that you got out. Just one thing to keep in mind. But KV cache reuse just means we had a conversation yesterday. I'm not going to ask you to repeat everything. I'm just going to, you know, take my notes and put it back and get ready to answer you. Think of it, that's a proxy there. OK, inflight batching, so early on, this is why VLLM actually became really popular, is because usually when a batch of requests came into the GPU, I had to wait till the longest one finished, and everybody had to sort of suffer for whoever asked the longest question. But now, on an iteration level, I can sort of evict and then get another request in immediately. So you're really trying to flush the GPU as much as possible. So this actually significantly increased results, and this is why this was a really cool thing. So the page attention papers is a good one to read. KV cache optimizations, think of it. So remember, KV cache, I showed it to you earlier, just a bunch of matrices. So we can actually start allocating memory. So yeah, page KV cache is like I'm going to allocate memory in uniform blocks versus just randomly allocating memory. And the reason why that happens to you is like, I don't know how big of a prompt someone's going to hit me with. So I have to, if I do it in a page way, I can sort of reasonably allocate memory instead of wasting things. And then quantized KV cache, page KV cache. You'll see this quantization thing everywhere. So there are different ways that you could, this is not a way people hustle. It's like they're trying to change the precision of each of the pieces of math so they can try to squeeze as much performance as possible. So quantized KV cache just means I drop the precision of those matrices. Quantization, everyone's going to try it. So pay attention to that accuracy loss. If you leverage FP8, you're not going to get pretty much minimal loss, right? But once you start getting into int8, int4, you will incur some accuracy loss. The thing I want you to pay attention to, what does this W and A mean? This means weights and activations, right? Activation is just the output of any sort of internal thing inside of a deep learning model or an LLM model. So weight 8 means this is int 8 and int 8. This means int 8 FP16, right? So that's when you read that type of documentation, that's what it means. DJ, I'm going to take the 5 minutes. You all good for 5 minutes, or you all need to eat? We're good? OK, I'm going to steal it. All right. This is another cool paper by Professor Song Han. He's a distinguished scientist at NVIDIA. I think he essentially invented FP8. So that's why it came into Hopper. And what's sort of cool, like his advisors, the head of research at NVIDIA. So that's also an interesting backstory for you PhD folks. So what's happening here? So what they realized was like, hey, I have, these are my activations, I have my weights, but quantization just says, I'm going to try to compress this range, right? So quantization is just range compression, but you want to maintain the things that you had in there before. So if you look at this, the activations had a lot of outliers. So it's very difficult to come up with a quantization scheme to accurately re-represent this same pattern in a lower range, okay? So, but you're seeing in the weights, there's like almost no outliers happening. So they noticed that, and they're like, hey, this is a matrix multiplication. Let's see how we can hustle with math, right? So mathematicians are really hustlers, I think. So I have my input data. So if you look at the dynamic range between -16 to, I think, 6. But if you look on this side, look at the range. So what they actually do is, this is what, 2. So the maximum is -1 or -2 to +2. So if you look, I actually just shift some of that range over to the weights. So if you look, I have a 4 to -4. So I kind of push some of the error or technically the outliers into the actual weights itself. But through that matrix match, it's actually a very simple thing. You're able to reduce this range of outliers here. So that's how they're able to sort of compress it. So this, when you look at smooth quant in the documentation, you'll be like, okay, I kind of know what's going on. Here's some of the benchmarks on it, right? So they look at both the sort of latency speed up. So this is 4 different models, so big models, small models, latency and corresponding memory reduction. We're always trying to get memory reduction as much as possible. So that's more of it on the intuition side. You may have heard of sort of NVIDIA NIM. That's just us really packaging this thing and getting it very easy to use. You download a container and you're ready to go. It has TRT-LLM, Triton, VLLM in there. The way that'll work, you pull a container. What we're going to decide is like, okay, what GPUs do you have in the system that you're currently running? We'll figure out what's the most optimized engine for that series of GPUs. We'll check, okay, is there a TRT-LLM engine? If not, we'll actually just go back and pull a VLLM engine for you. But the whole goal of that is to make sure that it's easy, you have enterprise support. This is what the architecture looks like. So you'll also have a TensorRT-LLM, both runtime and a VLLM runtime on top of Torch, so we're at Torch today. So you have an intuition there of what it looks like. We have LoRa support as well. So this example is just saying 3 requests, go to 3 LoRas, and you have an adapter cache. Essentially, we cache the LoRas on the GPU, on the CPU, push them to the CPU a lot faster. And if you do end up, I'll give you guys free GPUs, so I know that's why you're sticking around. It's free GPUs, so it was a good move up front. I have a couple of different types of GPUs. I figure out how much GPUs you have. We have this thing called a throughput engine versus a latency optimized engine. So if you ever want to increase the latency of your LLM system, just put more GPUs, it'll run faster. That's the impressive math. So the way that you read this is a Llama 3 8B instruct. I think this is a single H100 FP8 a throughput engine, right? So if you get to that stage, you can leverage it. This is a really good blog on how TRT-LLM could sort of save you a lot of money. Sorry if that was a little fast. Let me put it back. Okay. And then benchmarks. It's really important when you go to read benchmarks, I want you to see this pattern. So short, 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 long, short, longer, long, short, long, long. Right? So when you watch a benchmark, it's just not one number. You have to watch all of these use cases and match that to your deployment. Okay? So you could, this is also available online. And okay, so there's a free GPUs. Take it, have fun. So everyone is a free developer account. You get 1,000 inference requests for free. We work with all the different model providers. It has an OpenAI compliant API, so the same code you're running maybe right now. So I like to share it with folks so that you could go benchmark which open source model makes sense to you for free, like 405B. You could go get there. Like you could send 1,000 requests to 405B. So yeah, that's it. So Ankit, we'll be at the lounge. Okay, we'll be at the NVIDIA lounge if you guys want to chat, and we have a ton of engineers there. We can go as deep as you need to go. Thanks for coming.